everyone. You're watching the second part of the 20th lecture in the series Mathematical Methods for Economics. In the first part of the lecture, I walked you through the definitions of horizontal, vertical, and oblique asymptotes. And towards the end, we were talking about some guidelines which can be useful in establishing what your vertical or horizontal or oblique asymptotes will be. So just to summarize quickly before we get into our practice questions for this session. First of all, vertical asymptote is one for which the function tends to infinity or minus infinity as x tends to some vertical line x equal to a. And here, make sure that the function tends to infinity or negative infinity. There are not any holes in the function. Okay. As far as a rational function goes, if the degree of the numerator is less or equal to the degree of the denominator, if the degree of the numerator is less than the degree of the denominator, the line y equal to 0 is a horizontal asymptote. If the degree of the numerator and the denominator are equal, then it's coefficients of the leading terms in the numerator and the denominator, the ratio of those coefficients, that would give you the horizontal asymptote. And if the degree of the numerator is more than the degree of the denominator, and for our purpose, because we're not doing curvilinear asymptotes, if the degree of the numerator is 1 more than the degree of the denominator, then we have an oblique asymptote or a slant asymptote. So in this session, let's look at some questions because unless you practice, you won't really understand the concepts. So let's look at this example where the function, here we have a rational function, f of x equal to x squared minus 3 divided by 2x minus 4. And here, I haven't written the question here in the slides because there's one standard question for all the slides here, which is find all the asymptotes that exist for a given function. So you have to specify the asymptotes, and even if the asymptote does not exist, please specify, make the answer complete. Okay, so let's first look for the vertical asymptote. So as I said, the trick here is to look for, is to check for what value of x the denominator is 0. And here we see that the denominator is 0 for x equal to 2. But at the same time, make sure that the function tends to infinity or minus infinity because you don't want any holes in the function. So here we have that the limit of the numerator x squared minus 3 as x tends to 2 is not equal to 0. So clearly, because in the limit the numerator is not 0 and it's going to be something positive. So it's the limit as x tends to 2 of x squared minus 3 is going to be 4 minus 3, which is 1. So that when you take the limit of the denominator, that is 0. So the whole thing will in fact shoot off to infinity or minus infinity, depending on whether x approaches 2 from the right or from the left. Okay, so x equal to 2 here is the vertical asymptote. Now here, because the degree of the numerator is 1 more than the degree of the denominator, there is no horizontal asymptote, but there is going to be an oblique asymptote. So this also should send you the message that you can't have an oblique asymptote and a horizontal asymptote existing together for a rational function. And yes, there will be an oblique asymptote because our conditions here are satisfied. You have a rational function with the degree of the numerator 1 more than the degree of the denominator. So what is the criterion to find the oblique asymptote? You perform the long division where you divide x squared minus 3 by 2x minus 4. So let's see what happens when we do this division. Now 2x, when we divide x squared minus 3 by 2x minus 4, 2x will go into x squared, x by 2 times, right? Because 2x times x by 2 is x squared. Now once you take that in the quotient, that is going to give you x squared here, and minus 4 times x by 2 is minus 2x, so that's what I have here. And as you are familiar with any process of division, the sign has to be changed. So x squared and x squared will get cancelled. Here, this minus 2x will become a plus 2x. So when carried here, so it's going to be 2x minus 3. Okay. Now, 2x will go into 2x once, right? So 2x times 1 will give you 2x, and minus 4 times 1 is minus 4. So here the remainder is 1. Okay. So the oblique asymptote in this case is x by 2 plus 1. Now note here while you're writing the answer, so examine all three, the existence of all three asymptotes. And also, common mistake that students make in an exam is when you're asked about a vertical asymptote, they'll just write vertical asymptote is 2. No, specify the vertical asymptote in terms of the x coordinate. So vertical asymptote is x equal to 2. And let's say there is a horizontal asymptote. So horizontal asymptote will be y equal to something. So give the complete answer. And here in this case, the oblique asymptote is going to be y equal to x by 2 plus 1. So I've shown you a visual here. Right now, you're not set to draw this visual entirely on your own, but you can see towards the end of this course, you'll have all the pieces coming together. But at least I think you can get a sense of, in terms of what we've done in the course, you can get a sense of what the horizontal and vertical intercepts would be. And now you also know how to draw the asymptotes, because it's a linear asymptote. You can easily draw it, y equal to x by 2 plus 1, and the vertical asymptote here is x equal to 2. Okay. So as I said, there is an alternative way also of finding oblique asymptotes, or one would say how to argue it out, which is found in some textbooks. So when you perform this long division, you know that you can write x squared minus 3 by 2x minus 4 as x by 2 plus 1 plus the remainder 1 divided by the divisor 2x minus 4. So now when you write your rational function in this way and you apply the limit as x tends to infinity or minus infinity, you see that this second term here on the right, as x tends to infinity or minus infinity, the second term will tend to 0, right? And this function will then approach x by 2 plus 1, which is then our oblique asymptote. So if you just don't want to do things mechanically, that x by 2 plus 1, which is a quotient, is the oblique asymptote, you can just write things out logically like this from your long division, write out the result, and then apply the limit. You'll get the same answer. Let's look at the next example. That's a simple one where the function is 1 by x squared. Okay, so let's explore the asymptotes for this particular function. As far as the vertical asymptote is concerned, here you can see that we have a 0 for x equal to 0 in the denominator, and it's quite clear that as x tends to 0 from the left, because it's an x squared in the denominator, so it doesn't matter whether x approaches 0 from the right or from the left, regardless of which direction x approaches 0, the function tends to infinity. So x equal to 0 is a vertical asymptote. Now, what about a horizontal asymptote? Horizontal asymptote is saying what value does a function tend to as x approaches infinity or minus infinity. And clearly the limit of the function as x tends to infinity or minus infinity is 0. So here your y equal to 0 or the x-axis acts like the horizontal asymptote. Take this example where the function is 1 divided by x minus 1. This is also a simple example, by the way. So let me go back one slide again. Here you should have also reported no oblique asymptote. Okay. In this case also, you'll have to report no oblique asymptote. You have a vertical asymptote here at x equal to 1. So because it's x minus 1 in the denominator, as x approaches 1 from the right, this function will shoot off to plus infinity, okay? And as x approaches 1 from the left, because we'll get negative values in the denominator, the function will tend to decrease without bound. It will shoot off to minus infinity. But regardless, the point is that the vertical asymptote here is x equal to 1. What about the horizontal asymptote? The horizontal asymptote here would be y equal to 0, simply because the degree of the numerator is less than the degree of the denominator. So as x approaches infinity or minus infinity, the horizontal asymptote is going to approach the line y equal to 0. And you can see that in the visual here. Okay, now let's look at this example, which is quite interesting, and you will see that in a bit. This function is x cubed plus 2x squared minus x minus 2 divided by x squared minus 4. Now, if you notice, in this particular function, I can write the denominator x squared minus 4 as x plus 2 times x minus 2, okay? But be careful here, because what students typically tend to do is they report x equal to minus 2 and x equal to 2 as the vertical asymptote when asked such a question. But note here that there is a twist to the story. This function actually has a common factor. In the numerator, okay, this function has a common factor, and you can write the numerator as x plus 2 times x squared minus 1, okay? And you can always cancel out this common factor. Now, what happens here is, what does it mean when there is a common factor? The point here is that if you take x equal to minus 2 here, this fraction will collapse to 0 by 0, right? Basically, the limit expression here is an indeterminate form of the form 0 by 0. We haven't done indeterminate forms, but we'll be doing that in a couple of lectures. So here what happens is that if I take the limit as x approaches minus 2, because of this common factor, this common factor will get cancelled. So the limit is not plus infinity or minus infinity as x approaches minus 2. When you cancel out these factors, you can substitute minus 2 here in the denominator, you'll get minus 4. And when you substitute minus 2 in the numerator, you'll get 4 minus 1. So that's basically minus 3 by 4. So this is to say that as x approaches minus 2, the function is tending to minus 3 by 4, not infinity or minus infinity. So that can't be a vertical asymptote, because that will violate the definition of a vertical asymptote, which is to say that the function should tend to infinity or minus infinity. So look out for common factors, okay? And at the same time, make sure that the function tends to infinity or minus infinity, or does not tend to minus infinity or plus infinity, for establishing whether or not a vertical asymptote exists. So in this case, you don't have a vertical asymptote for x equal to minus 2. I hope that argument is clear. But yes, for x equal to 2, we're going to have a vertical asymptote, because the numerator, once you cancel off x plus 2 in the numerator and denominator, the numerator is going to be 4 minus 1, 3, which is non-zero, and that is then divided by 0 here. So this function is going to shoot off to infinity as x tends to 2. And in particular, as x tends to 2 from the right, let me show you the visual. As x tends to 2 from the right, it's going to shoot off to plus infinity. As x tends to 2 from the left, it's going to shoot off to minus infinity. Also, because the degree of the numerator here is 1 more than the degree of the denominator, okay, this function will not have a horizontal asymptote, but it will have an oblique asymptote, okay. So let's see what the oblique asymptote is going to be. Let's perform the long division here. So as I was saying, because there's a common factor, the fraction boils down to x squared minus 1 divided by x minus 2. So that's just more tractable. So let's perform the long division for x squared minus 1 divided by x minus 2. And here you can see that x goes into x squared x times. So you have an x squared here. Minus 2 times x will be brought here, right? So the sign of that will change. That will be brought here as 2x. and you have a minus 1, which will be carried down as minus 1. Okay. Now, x will go into 2x 2 times. Okay. So, that's 2x here, which you're going to write here. And then minus 2 times 2 is minus 4. So, you have a minus 4 here. And then when you change the sign of this line here, so 2x minus 2x will get cancelled. Minus 1 plus 4 is going to give you a 3. So that is where your process of division ends, and you have a remainder of 3, but your quotient is x plus 2, which then is your oblique asymptote. So y equal to x plus 2 is the oblique asymptote. So look out for common factors, but at the same time, look out for the function. The more important criterion is to check whether the function tends to infinity or minus infinity, because if you notice, let me just finish this part. So this was a visual for this particular graph with x equal to 2 as the vertical asymptote, and you can see here that there is a hole. So as I was explaining, for x equal to minus 2, there is the function does not tend to infinity or minus infinity, but it tends to this particular value, which we found out to be minus 3 by 4. So that is what you have here. It's a hole in the function. So what I was saying was that, cancel out your common factors, but be careful, because, so this is something for you to think about. So I have just manipulated this function a little bit. So you have x by x squared. Now, if you have x by x squared, I can ask you, does this have a vertical asymptote? And the answer is yes. So even though you might cancel out the common factors, remember that you're still left with an x in the denominator. So, so here, yes, x is not equal to 0. The function is not defined for x equal to 0, but as x tends to 0, it will be, the function will shoot off to infinity or minus infinity. If x tends to 0 from the right, it will shoot off to infinity, and as x tends to 0 from the left, it will shoot off to minus infinity. Okay. Yeah, let's look at another example. So here you have f of x equal to 2x cubed minus 3x squared plus 3x minus 6 divided by x squared plus 1. Because the denominator is not 0 for any value of x, there is no vertical asymptote. There is no horizontal asymptote as well, because the degree of the numerator is more than the degree of the denominator. You can't have a horizontal asymptote or limit at infinity here. So as far as an oblique asymptote is concerned, yes, there will be an oblique asymptote. And again, you perform the long division here. And once you, x squared goes into 2x cubed 2x times. So you have 2x cubed here. And then 2x times 1 is 2x. So that's why you have a 2x here. I was not observing it carefully. So yeah, you have a 2x here, and the sign here will change. So that will give you minus 3x squared. And 3x minus 2x will be x, which is carried down as x minus 6. Yeah. And then x squared goes into minus 3x squared minus 3 times. Okay. X squared minus 3. X squared times minus 3 is minus 3x squared, okay, and plus 1 times minus 3 is minus 3, so you have a minus 3 here. The signs of these two terms will change, so that minus 3x squared plus 3x squared will get cancelled, and you'll have x minus 6 plus 3, which is x minus 3 in the remainder. So the oblique asymptote here is 2x minus 3, and the second part of the question asks you, does this oblique asymptote or does a function have any point of intersection with the oblique asymptote? Now, note here that the function can be written as the quotient, which is 2x minus 3, plus the remainder x minus 3 divided by the divisor. So the question is, does a function have any point of intersection with the oblique asymptote? And here the answer would be yes, because when you equate this expression for the function written in this way to 2x minus 3, which is your expression for the oblique asymptote, you can see that 2x minus 3 gets cancelled on both sides, and this gives you an intersection point for x equal to 3. So yes, there is a point of intersection, which is x equal to 3, and as you can see, for x equal to 3, the value of y is 6 minus 3, which is 3. Okay, We'll do one more variant. This is also an interesting variant for calculating asymptotes. So here you have the function, which is a function of n, which is square root of n squared plus 16 divided by 8n. Okay. First of all, look at this manipulation. It's an interesting manipulation because I can take n squared common and write the numerator under the square root as 1 plus 6 by n squared, right? And when I take the n squared out of the square root, remember by definition, square root of n squared is the absolute value of n, okay? So depending on whether n is positive or negative, note n can't be 0, you can't have division by 0. So if n is positive, then absolute value of n would be n itself. The n's will get cancelled. This is the expression you'll be left with. Whereas if n is negative, you'll be left with minus of square root of 1 plus 6 by n squared divided by 8. So this then gives you n equal to 0 as a vertical asymptote, because you can see here that as for a positive, as n approaches 0 from the right, this function will shoot off to infinity. As n approaches 0 from the left, the function will shoot off to minus infinity. The question now is, does it have an oblique asymptote or a horizontal asymptote? So look here, there is definitely a horizontal asymptote, because if n approaches infinity, right, remember our manipulation is where we are writing the function as mod n times square root of 1 plus 6 by n squared divided by 8n. So if n approaches infinity, we're talking of a large positive number. So absolute value of n will be n itself. So the n's will get cancelled, right? And this you can see that as n approaches infinity, the function is going to approach 1 by 8. And similarly, as n approaches minus infinity, the function will approach minus 1 by 8. So there are two horizontal asymptotes for this particular function. And you can see the visual here. There is no oblique asymptote here because the criteria that we have talked about are not fulfilled here. We have to have a rational function first of all, and we have to have that degree varying like that. So the difference of the degrees being 1, so none of these conditions are fulfilled. You can see the picture here. You can see that two horizontal asymptotes and one vertical asymptote. So this is a question for you. This is also a question we had done partly in the previous lecture, where the function is x squared minus 25 divided by x minus 5. Note here again, at x equal to 5, the function collapses to the form 0 by 0. The limit expression is an indeterminate form. Here, if we take the limit as x tends to 5, this function does not shoot off to infinity or minus infinity. Actually, the limit, if you remember the discussion that we had, the limit of this function as x tends to 5 is 10. So go back to the previous couple of lectures that we did on limits and asymptotes, and here don't make the mistake of classifying x equal to 5 as a vertical asymptote, okay, because the limit here is 10. There's a common factor here again, which actually gives us this whole at x equal to 5. And now some food for thought for you. Would this function have an oblique asymptote? That is something for you to think about. And the way to think about is in terms of the definition, because we have laid down the definition as such that the vertical distance between the function and the oblique asymptote should tend to 0 as x approaches infinity. So think about that definition, because here clearly you have a situation where where the way things are presented here, the degree of the numerator is 1 more than the degree of the denominator. So think about whether this function will have an oblique asymptote. Okay, this is a question from one of the Delhi University exams. It's again a kind of interesting question. So this asks you, find the condition on M such that the asymptotes of the curve y equal to 2 times m minus 1 x minus m plus 1 divided by m plus 3 times x plus m intersect at a point above the line y equal to 2x minus 1. So here you can see the vertical asymptote where your denominator becomes 0, and make sure your function is tending to infinity or minus infinity. So x is equal to minus m upon m plus 3. That is where the denominator is 0. and there's no problem, there are no common factors here, so this will be a vertical asymptote. Horizontal asymptote will be the coefficients, because here the degree of the numerator is the same as the degree of the denominator. So 2 times m minus 1 divided by m plus 3 will be your horizontal asymptote. And then the question is asking you what will be the conditions on m such that the two asymptotes, the vertical asymptote and the horizontal asymptote, intersect above the line y equal to 2x minus 1. Okay, so our x here is minus m upon m plus 3. So basically we want our y value for the horizontal asymptote, 2 times m minus 1 divided by m plus 3, to be more than 2 times minus m divided by m plus 3 minus 1. Okay, because you want the intersection to happen above this y value. So once you do the algebra for this, you'll find that the condition is 5m plus 1 divided by m plus 3 is strictly greater than 0. You can work out the algebra on your own. Then let me do one more last example with you. This example also you can try on your own. Here there's a common factor, so be careful. And this last example is also something you can try. It's mod x plus 1 by x. And here, this is how the function breaks up. For x positive, it's x squared plus 1 by x. For x negative, it's 1 minus x squared by x. So here you have x equal to 0 as the vertical asymptote. The function tends to infinity as x tends to 0 from the right, and it tends to minus infinity as x tends to 0 from the left. Okay, so oblique asymptote here is y equal to x and y equal to minus x. This is what you get when you perform the long division. So this example is interesting because it shows that you can have two oblique asymptotes, which is what I've shown here. This is the graph is in blue, the curve is in blue, and you can see that there are two oblique asymptotes here and also a vertical asymptote at x equal to 0. And that's all we have for today. I hope you found this discussion useful. Thank you.